Hi everyone, in this video, I will explain how to determine the effective dimension of the foundation to calculate the ultimate bearing capacity for two-way eccentricity loaded foundation. What is eccentricity? So as you can see here, we have the concentric and eccentric footing. This is an example of the concentric footing. You can see that the column was situated in the middle of the column footing. However, on the other hand, we have the eccentrically loaded column foundation. You can see that the column is not located right in the middle of the column footing and is at the boundary or at the end of the wall, and it's normally due to the adjacent wall next to the loading and footing. So what happened here in eccentric footing is the center of gravity of load not coincide with the center of the gravity of footing. Okay, this is the plan view of the footing. You can see that the center of gravity of the footing located in the middle in the point in red color. And you can see that the positions of the column load is not in the middle of the footing. Alright, so you can see that the center of gravity for the column load in the yellow color here. So there is a gap or there is a distance between center of gravity and footing with the center of gravity of the load. So this is the eccentric. So the symbol for the eccentric is E in a distance. Okay, it is a distance. Alright. Okay, so now the eccentric is actually can happen in only one direction, so also known as unaxial eccentricity. It can be in x-axis in x directions, or it can be in y direction. As you can see here, alright, so if the center of gravity of loading separated in x direction, like just as you can see here, so this is in x direction. However, in along the y-axis here, you can see that this is the center of gravity for the footing, but then this is the column. Alright, and the center of gravity of the of the column load somewhere here. So we have the eccentric in y direction. So we need to take into account the eccentric direction in order to determine the ultimate bearing capacity. Besides in axial eccentricity, they also have the biaxial eccentricity. Okay, it means that the directions of the eccentricity in two direction, x and y axis. Alright, so I want to show you how we determine the two directions of eccentricity from the layout. So this is the column. Alright, this is the column. And we have the area of the footing. Alright, the center of the gravity for the footing, okay, it should be in the middle of the footing here. But then we have the column at the corner side here. And the center of the gravity for the column load is somewhere here. Alright, so now you can see that we have eccentricity in both direction, in the x direction, and then to the y direction. So this is an example of biaxial eccentricity in both direction, y-axis and x-axis. Beside label it as eccentricity in an x direction, okay, beside labeling it as ex and ey due to the directions of x and y, it also can be labeled as eb and el. Eb is a direction in a with direction. Alright, so it also is actually the ex. And el is the direction in a length direction. L is for the length, which is the in a y direction. So the eccentricity can be determined from this equation due to the moment to the load for both direction, y and x. Before we proceed with the ultimate bearing capacity, we first need to identify the effective dimension. The effective dimensions of the foundation. To determine the ultimate bearing capacity of the two-way eccentricity loaded foundation, we will use the effective area method by Meyerhof 1953. That we need to determine the effective dimension of the foundation before you proceed with the ultimate bearing capacity. However, for the two-way eccentricity, there are few cases that we need to consider to determine the effective dimension. Okay. According to Heiter and Enders 1985, they come up with the 5 possible cases in order to determine the effective area, effective width, and effective length of the foundation that will be used to solve or to get the ultimate bearing capacity. There are 5 possible cases that the case will depends on the EL over L and EB over B. So as you can see here for the case number 1, the conditions or the requirement is that the EL over L more or equal to 1 over 6 and this is N, alright? EB over B more or equal to 1 over 6. Then we need to determine the effective area, which is A prime equal to half times B1 and L1. So we need first to identify the B1 and L1. As you can see, due to the eccentricity, the effective area that we need to consider to get the Q ultimate is in this form. So that's why we need to determine the B1 and L1. Alright, so this is equation come up by Heiter and Enders. So this is how we get the B1 and how we get the L1. This one is quite straightforward because there is an equation. So let's move to the case number 2. For the case number 2, the requirement is EL over L is less than 0.5 and EB over B in the range that more than 0 but then less than 1 over 6. So the effective area, this is the effective area that we need to get the L1 and the L2 first. Okay, so as you can see that the effective area for this kind of requirement. So how to get the L1 and L2? Okay, so there is a plot or there is a figure, alright, by Heiter and Enders. Okay, in order to get the L1 and L2. So I want to show you how to use this figure to get the L1 and L2. Alright, so how to use this figure to determine the L1 and L2. So we have an example data with the EL, EB, and the L and B, and the ratio of EL over L and EB over B. So now we have EL over L 0.2 and EB over B 0.05. So firstly, you look at the figure, you look at the diagram. Alright, so it's divided into 2. You can see that the black point here, in a black color point here, arrow to the right side will give you the regions of L1 over L. Alright, so to the region to the right side is to obtain the L1 over L ratio. And then arrow to the left side is the region for L2 over L ratio. So means that to get the ratio of L2 over L, you will refer to the left side of the figure. Okay, now you look at the EL over L. So now we have the EL over L is 0.2. Okay, now you look at the diagram here. In the y-axis is the EL over L. So we have 0.2 as given EL over L here. You draw a horizontal straight line. And then now we need to refer to EB over B. Okay, we have both side value of EB over B. Okay, EB over B on the top at the right side is for region to get L1 over L, and EB over B at the lower part on the left side is to get the L2 over L. So now we need to identify where is the line of EB over B for 0.05. As you can see here that we only have 0.04 and 0.06. Obviously means that in the middle of 0.04 and 0.06 is 0.05. So we will draw or sketch another line in the middle to indicate that is 0.05. So we start with the L1 over L ratio. So now look at the intersection point. Look at the intersection point between the horizontal green line here with the dash red line here. Okay, you can see there is an intersection here. Going down and read through at the x-axis here to get what is the value, what is the ratio of L1 over L. You can see that you have a roughly estimate is 0.75 since this is 0.7, so this is 0.75 for the ratio of L1 over L. So you have this ratio L1 over L. Then you can solve this one since we have the L value here is 2 meter. So the L1 is 1.5 meter. Okay, then we go to the left side. Alright. And then we need to identify the line for 0.05. Again, what we have is 0.04 and 0.06. So we need line for 0.05 in the middle. Alright. So find an intersection point between the green line horizontal here with the dash red line. Alright. So there is an intersection point going down and read through at x-axis. So we have 0.4 for the ratio of L2 over L. Again, you can solve this one since we have the L. So the L here, L2 here is 0.8. So when you have L1 and L2 just now, so you can use that L1 and L2 to get the effective area. Then after that, you can determine the effective width B prime and also the L prime. So that is for the case number 2. Okay, so this is the case number 3. You can see that the requirement is EL over L is less than 1 over 6 and EB over B in the range of more than 0 but then less than 0.5. Now you look at the effective area A prime that we need half times with B1 plus B2 times with L. So we have the L, the size of the foundation, but we don't know what is the B1 and B2. This is the effective area. Alright, the effective area for this kind of condition. Okay, so now we need to determine what is the B1 and B2. Again, Heiter and Enders come up with this figure to get the B1 and B2. What is the difference between this one with the case number 2? You can see that for the case number 3, this figure at the y-axis, it has EB over B. And in a y-axis, in x-axis, we have the ratio for B1 over B and to get the B2 over B. Okay, so how to use this figure to determine B1 and B2 is actually similar with the case number 2, but different axis title. So we have EB over B. Previously in case 2, we have EL over L. Also, in this case number 3, we have the ratio for B1 over B and B2 over B. In previous case number 2, we have L1 over L and L2 over L. So how to use this diagram is exactly similar with the previous one. So we have on the right side is the region for B1 over B and on the left side is the region for B2 over B. So you have the EB over B 0.2, identify it in a y-axis and then draw a horizontal line and then look at the EL over L. So we need to identify the EL over L. Okay, and the line is 0.03. Again, there is no line for 0.03. So we need to add another line. Okay, obviously it will situated in the middle of 0.02 and 0.04. Now we have the dash red line. Okay, look at an intersection point. Going down, so you will get the ratio for B1 over B. So it's roughly around 0.68. So you can solve this one since we have the B is 2 meter. So the B1 is 1.36. And then we look at the left side to get the B2 over B. Again, you need an extra line for 0.03. Look at for the intersection point. Now you're going down and read through. So we'll have 0.47 for the ratio of B2 over B. Okay, you solve this ratio and you will get that B2 is 0.94. So once you have the B1 and the B2, so you can calculate the area and you can use that area to get the B prime. Okay, by using this equation, and also you can get the L prime. So that is for the case number 3. Okay. So now let's continue with the case number 4. So this is for the case number 4. Alright, you can see that the requirement that EL over L is less than 1 over 6 and EB over B in the range of more than 0 but less than 1 over 6. Look at the effective area. So what we need to determine, what we need to identify before we proceed. So we need to have the L2 and also the B2. Okay, so how to get the L2 and B2? So again, we have another figure to refer to get the L2 and B2. So I will show you how to use this figure. Okay, so this is the figure that we need to refer to get the B2 and L2 for case number 4 in order to get the area. So we need to determine first the B2 and L2. So now we have an example of the data and the EL over L is 0.067 and EB over B is 0.05. Okay, to get the B2, alright, so you will need to refer to the ratio of B2 over B. So it can be determined by using the EL over L curves that slope upward. Alright, that slope upward. Alright, so this is the slope upward. Okay, for obtaining B2 over 2. Okay, this is the slope that facing upward. Alright, so we will refer to this slope curve, okay, to get the B2 over B. Okay, now example here. So we have the EL over L is 0.067. Okay, so now what we have is 0.06 and 0.08. Okay, now where is the 0.067? So we first identify where is 0.07 to roughly estimate later the 0.067. Okay, let's say in the red line here is 0.07. So we can roughly estimate that the dashed red line here is 0.067. Make sure that your estimations is relevant. Alright. You can put it in the middle because it will show you it is 0.065. Alright, so make it a little bit towards the 0.7. Okay, so you can assume that the dashed red line here is 0.067. Okay, now you need to refer to the EB over B. Okay, EB over B is 0.075. So EB over B, okay, at y-axis. So roughly estimate, okay, make sure it's relevant. So we have 0.05, 0.1 here. So this is where is 0.075. Draw a horizontal line, okay, as you can see here in a pink color, and then look at intersection point between the 0.067 with the 0.075. Okay, going down and then read through at x-axis here. So this one is to get the ratio for B2 over B. So it's around 0.42. So you have this one, B2 over B is 0.42. You solve this ratio, then you can get the B2 exactly 0.84 meter here. Now, we want to determine the L2. Right. So for the L2 over L ratio and to get the L2, we need to refer the slope downward of EL over L curves. Alright, so the slope downward, as you can see here, alright, there are a few lines that indicate the slope downward. So you will refer to that one. So now we need to identify the EL over L 0.067. Okay, refer to the downward slope. Okay. Alright, we have 0.06 and we have 0.08. Okay, curve that slope downward. So we need to identify roughly where is 0.07. Then we can determine where is the 0.067. So let's say in the green color here is 0.07. Okay, now we can add another line to estimate where is the 0.067. Okay, let's say the dash green line here is 0.067. Okay, so now refer to EB over B is 0.075. Look at an intersection point. And going down, now you can get the ratio for L2 over L. So it's around 0.31. Okay, and then you can solve this one since we have the L is 3 meter. So the L2 is 0.93. So once you have the B2 and L2, you can use that one to get the effective area. Then from the area, you can use that area to get the B prime and the L prime here. That is for the case number 4. And finally, for the case number 5 is the circular foundation. Only for the circular foundation. Note that the circular foundation, the eccentricity loading is always in a one-way direction only. Alright, as you can see here, okay, ER over R is the radius. Okay, so to get the effective area and the effective width, we can refer to this table. Okay, that you have the 3 columns here. Ratio of ER over R, A over R square, and B prime over R. Alright, so let's say you have the ER over R is 0.7, then you can have the A over R square is 0.62 and B prime over R is 0.37. Alright, once A prime and B prime determined, so you can get the L prime. Because we will know the R, the radius of the foundation. So you can get the A prime and B prime. Okay, once you complete the effective dimension. Okay, once you know the effective dimension. Okay, once you know the effective dimension, then we can proceed to get the ultimate bearing capacity. Okay, we already have the B prime and L prime. So we can proceed with the ultimate bearing capacity by using the Meyerhof equation. Then you can get the ultimate load of the foundation. That's all. Thank you.